Welcome back to the classroom. My name's Mr. Wong. So in the last lesson we talked about, we were looking at force analysis diagrams for circular motion. So what I'd like you to look at now is actually perform some calculations using these scenarios here. Okay, so let's begin. This is the calculation problems of the executing uniform circular motion PowerPoint slide. So let's begin with this question here. We have a 2-ton, and so that's our mass. Let's just change our color. So that's our mass here. Goes around a curve of radius 150 meters at a velocity of 12. So that's our linear velocity. Calculate the sideways friction between the road and the truck. So this is for our curved horizontal motion. We know that the centripetal force and the net force is equal to the net force, and that's contributed by our friction force. Okay. In this case, the sideways friction, to find the sideways friction, we can use the formula for centripetal force, because for an object spinning or rotating around a curved flat road that is, we can simply use the centripetal force formula. Okay, it's quite wordy, but I'm only doing it for this particular case, just to make it really obvious for everyone. And then we just do our substitution. So 2 tons is 2,000 kilograms. Hopefully you remember to convert your units into the appropriate SI unit equation. The velocity we're moving at is 12 squared. Divide that by 150 meters. And so we get an answer of 1,920 newtons. And remember, force is a vector, so we're moving towards the center. So that's what we have. Okay, next we have is B, calculate its centripetal acceleration. The formula is v squared over r. So again, using the same values, 12 squared divided by 150, we get 0.69 meters per second squared. And this is also moving towards the center of our radius. Okay. And then C, calculate the angular velocity of the track. So the formula we can use, we want to find omega. We have linear velocity and we also have radius. So V over R. Okay, so it would be 12 divided by 150 and we get 0.08 radians per a second. If you were to try and get this in degrees per second, you'd have to convert it. And to do that conversion, again, like we talked about before, let's actually show that very quickly. So if I was to convert this into degrees, I simply times this value that I have here by 180 over pi, and I would actually get about 4.58 degrees. Okay, so well, let's do that again. Degrees per a second. So that would be the angular velocity. So that's our first problem. Let's move on to our second problem. Okay, again, a curved horizontal road question. So let's see what we have here. We have a mass, we have a radius, remember. This is in kilometers, so let's just, for our own sake, convert that into SI units first. Constant linear speed, so that's V. So what is the angular velocity? Again, we have V, we have R, so omega equals to V over R. So 26 over 1,000, so it's 0.026 rads per second. we have b. What is the centripetal acceleration? V squared over r. So 26 squared over 1000, 0.676 meters per second squared towards center. And then what's the force on the car? So the cause of the centripetal acceleration is obviously the centripetal force, but obviously our centripetal force is caused by the friction on the road. So these are relatively straightforward. Essentially, you just need to find the correct formula to substitute your values in. If you can do this, then awesome. If you are having issues with that, then I'd suggest you just try the questions again at the start of the video and see how you go. And so that's how you do question 2. Okay, let's go to question 3. Okay, so question 3 is now on banked roads. So what we mean by banked road is this one here. So if an object is undergoing uniform circular motion, but on an angled road, we have our radius. Let's just link every information we have. We have our angle and we have our mass. Calculate the net force acting on a cyclist at this instant if they are riding at the design speed. Okay, so we want to find the net force, meaning by this force that's going in the center. So this force going in this particular direction. Now, I've already given you the hint of how to do this question, but for those who are interested in actually trying to work out how to do that calculation, think of it this way, okay? If we redraw our force diagram, we have gravitational force coming down from our moving cyclist. If you actually have a look at where the net force is, the net force is, in a way, the horizontal component of these two vectors, right? So if I draw my triangle out like so, I have my net force down here, my angle 42 degrees. That's where we get the tan theta from. As you can see, we have the adjacent side and we have the opposite side here. Okay, so what you can do first is do the appropriate substitution. So we know it's tan 42 equals to the net force divided by the gravitational force, which is mg. So m is the mass, that's 75. G is the acceleration due to gravity. You notice that I didn't actually put a plus or minus here. Now technically, because we are trying to find a force, we should. But in the case of the net force for uniform circular motion, we know that the motion is going towards the center. So, you know, all you really need to do is just write towards the center. The other reason why you can't really use a plus or minus in this calculation is you're looking at two different vector directions. What I mean by that is gravitational force is going up or down, or it's looking at the vertical component, and net force is looking at the horizontal component. So there's simply no way you can do that comparison. Okay, so now I can rearrange my formula. So net force is equal to tan 42, okay, times 75 times 9.8, and that gives us a value, I'll write it over here, 662 newtons to the center. Okay, so there's that. The last one we need to calculate is the design speed of the track. Again, this is our formula that we can use to work out the direction. But in case you not sure how to get to this equation because it's not given to you on your data sheet, then you can try and derive the equation for yourself to get to this same point. So again, you can see in this equation that we have here, so tan theta f net fg. So let me show you how we derive that I'm simply using this component that we have here. So it would be f net is equal to fg times tan theta. F net is centripetal force, so we can rewrite it as mv squared over r equals to mg times tan theta. Okay, you can see that. M and M divides each other. We move r over, so we get v squared equals to rg tan theta. And if we want to find it from there, rg tan theta, voila. Okay, so that's how you get that. Now let me just scribble that out so I can do the calculation. Okay, so that's scribbled out. And I'll write it down. So now we do our substitution. The radius we have is 50. Acceleration due to gravity is 9.8, or the value. And then tan 42. So we get a design speed of close to 21.0 meters per second. Okay, and that's how you do this. All right, and our last example. So we have a car with a mass of 1,500, horizontal speed of 880 kilometers per hour. So make sure you convert that into meters per second. You should find, if you divide by 3.6, the golden number, you have a velocity of about 22.2. So what is the net force acting on our car? So we have tan 10 times mass times acceleration due to gravity. So 1,500 times 9.8. So we get a value of 2,592 towards the center, don't forget. What radius of curvature must the road have so that the car can turn the corner with no friction force acting on it? So here we're actually trying to find the design speed, okay? So this is the formula we use. Remember, that was the derivation we did in the last slide, so that's what we have. So if we substitute that in, we have a radius, or we're actually trying to find radius, sorry. So all we have to do is just rearrange this over. So it's just r equals to mv squared over f net. You could substitute the values in first if you wanted to. That's probably more ideal for a HSC marker. So 22 square, remember the 22 is converted from the 80 kilometers. And then our net force. And so our radius is about 285 meters. Calculate the maximum velocity. Now this time we're looking at design speed. If our radius and angle are like so. So our radius 150 times acceleration due to gravity times tan 10. And our design speed would be about 16.1 meters per second. Okay, so there's that. All right, so that brings us to the conclusion of this lesson officially, now that we've gone through the calculation problems. Again, if you like the style of splitting theory and calculations, give this video a like. If not, still give it a like, give it some support, and I will see you next time. We'll talk about more stuff circular motion related.